All right, 10.6, the binomial theorem. Before I get into that, let's look at 10.5 again really quick to review. So we're not going to look at the second one here, but we're going to look at the first one. So go ahead and do number one. Pause the video, do number one. Okay, so here we go for number one. It says to find the first 5 terms of the sequence. Well, they give us term 1, right? A sub 1 means the first term. So -4 is my first term. They want us to find the next 4. Okay, so in order to do that, we're going to use this recursive formula here. So I always start with plugging in 1 to find my next term whenever I see an n plus 1 here. Okay, so if I plug a 1 in to that, I would get a sub 2, which means second term. That's what I'm looking for right now. This is a sub 2, this is a sub 1, a sub 3, a sub 4, a sub 5. Right, so to find a sub 2, I plug a 1 in for n, which means this whole thing is the same thing as just saying the previous term, right? The previous term times 2 minus 6, right? So, because if I plug a 1 in for n, this is just saying a times 1, right? So essentially, this is just the same thing as saying 2 times the previous term minus 6. Okay, so I'm going to just follow that pattern. 2 times the previous term, which is -4, minus 6, gives me -8 minus 6, which equals -14. So a sub 2, -14. All right, if I want to find a sub 3, you would plug a n equals 2 in, right? So a sub 3 would be equal to the second a sub 2 term times 2 minus 6. So again, that's just the previous term. 2 times -14 minus 6. When you do that, you get -28 minus 6, which is equal to -34. Right, so then we find the next one. 2 times -34 minus 6. 2 times -34 is -68, minus 6 is -74. Okay, so then I plug that guy in. 2 times -74 minus 6. When I do that out, I get -154, and I am done. Okay, so be comfortable finding the first 5 terms of a sequence given a recursive formula. All right, moving on to today's lesson, 10.6, binomial theorem. The binomial theorem is a very famous theorem, and it's based on this pattern that arises when we expand binomials. Okay, so expansion of binomials have all sorts of applications, a lot of them in computer science, some even within economics and how an economy might work. But anyway, let's at least look at the basics. I'm not going to get into too much with these. I'm just going to do the first couple of examples and get you guys used to the binomial theorem. So here, if you were to expand this out, remember that anything to the 0th power, notice we're taking a binomial to a power. Anything to the 0th power, though, just gives you 1, right? So that's just equal to 1. If you take the first power, it's just multiplying this whole thing by essentially nothing, right? It's just the first power, so we're not multiplying it by itself or anything yet. So in this case, we just would get x plus y, right? Then we go to this one where when you square that out, you would get, remember this pattern that arises. If you square, you have to FOIL it, right? So this is equal to x squared plus xy plus xy plus y squared, which is equal to x squared plus 2xy plus y squared. Okay, so there is a pattern that is going to arise with this, okay, with both the variables and with the coefficients that are out in front of the variables. Okay, so just notice that. So we're going to go to the 3rd power here. So what I'm going to do is I'm going to take the second expansion, x squared plus 2xy plus y squared. That's just this guy. And then I'm going to multiply it by another x plus y. So when I do that, I have to distribute it out, right? So this is equal to x to the 3rd plus 2x squared y plus xy squared. Okay, and then I'm going to keep going here, plus x squared y, now I'm doing the y values, distributing those out, plus 2xy to the 3rd, okay, plus y to the 3rd. Then I'm going to combine like terms. Okay, so We have x to the third, that can't be combined, but we have this x squared and this y here, right? So remember that the powers have to be the exact same, so x squared y term. We have 2 here, 1 here, so that's 3, so plus 3x squared y. Okay, that takes care of this, that takes care of this. Then we have an x, y squared term, and I believe, did I do this? Oh, this should be to the second power, my bad. There's 2 of those, right? So we have plus 3x y squareds, and then those are gone, and then I'm left with plus y to the third. Okay, so what I want you to notice right now is the coefficient pattern. Okay, so notice on round 0, we just had a 1, right? It was just equal to 1. On round 1, the coefficients of x plus y would just be 1 and 1. Okay, so this was round 0, this was round 1, first power. If I took things to the second power, I got this guy. So the coefficients would be 1, 2, 1, right? Then if I go to the third round, I plug this guy in, the coefficients are 1, 3, 3, 1. So 1, 3, 3, 1. I don't know if you're starting to see a pattern here, but I'm going to point it out, and you could use it. Now this would take a lot of time to just keep this pattern going, but we could just keep, so now we could multiply this guy by x plus y, but it just keeps getting longer and longer. But hopefully you'll see a pattern. Okay, so the 1s just keep going down, right? The 1s are on either side always. We always end with a 1. Then what we're doing is we're adding the 2 pieces, every 2 pieces together. So 1 plus 1 gives me the 2. 1 plus 2 gives me the 3. Okay, 2 plus 1 gives me this 3, and then 1. So then on my next round, I would have 1 plus 3, which gives me 4. 3 plus 3, which gives me 6. And then 3 plus 1, which gives me 4. So if I were to expand this out the next time, without doing it now, I can use my pattern, right? Without doing this whole expansion out, I actually know what it is. And I don't know if you've seen, I don't know if you see the other pattern that's arising with the variables. Notice my x term is going 3, 2, 1, disappears. My y term disappeared, 1, 2, 3, right? So just to show you what this would look like here, if we were still doing x plus y to the 4th, we'd start out with 1x to the 4th, okay, plus 4, and this is only plus because we have a plus sign here, but we'd have plus 4x to the 3rd. Notice that one dropped down a power, y, right? So this would be like y to the 1st power. Then we have plus, I'm using the 6 now, 6x squared y squared, okay, plus 4, so I'm going to this guy here, 4x y to the 3rd plus y to the 4th. Okay, every single time the powers are going to add up to the row that I'm on. So this is the 4th expansion. I have a 4th power here. I have 3 plus 1, which is 4 there, 2 plus 2, which is 4 there, 1 plus 3, which is 4 there, and then this guy, right? So in doing this, Pascal was first expanding a bunch of these out, and he found this pattern and created a triangle. And I've uploaded that triangle for you on Classroom, so you guys can check that out. It starts just like this, but it keeps going, just keeps going. I think I gave you one that goes up to like round 13 or something like that. Okay, so we can, for the first one, they want us to use Pascal's triangle. Okay, so if you were to, so I'll show you really quickly, like if you don't have access to it, we can just Google it, right? So notice that we have a C and a D instead of an X and a Y here, but now what I'm going to do is